Imagine getting this problem, maybe like a take-home exam question, where you know everything about the atoms in some material, every single detail.
Hmm.
And then you find out that when they all get together, they somehow create these completely new, bizarre particles that you just couldn't predict from looking at the individual bits.
Yeah, it's a fantastic thought experiment and really gets to the heart of what we're exploring today.
So today we're diving into one of physics' really deep, maybe slightly weird mysteries, how the whole system can be fundamentally more, maybe even different, than just adding up its parts, especially when we're talking about reality itself.
That's exactly it. We're focusing on fractional quantization, and it's a concept that genuinely makes you rethink how we understand matter.
And we're drawing on insights from a Nobel laureate here.
We are pulling directly from their work to sort of uncover these surprising ways nature cooks up its own particles almost, particles with these strange fractional properties. It's maybe a shortcut to grasping a pretty big paradigm shift in physics.
Okay, let's jump in then. For ages, science has leaned heavily on reductionism, right? Break things down, smallest parts. Understand those. Understand the whole.
And it's been incredibly successful, no doubt about it. We wouldn't be where we are without it.
But the sources we're looking at argue pretty strongly that while reductionism is crucial, it's not the only way to look at things. Some of the biggest phenomena, you just can't derive them from the tiny equations alone.
And that's where this idea of an emergent phenomenon comes in. That's the real twist, and honestly, the most exciting part for me.
Emergent phenomenon. Okay, unpack that a bit.
So think of it as a truly collective effect, like a huge murmuration of starlings. The whole flock move like one fluid thing, making these incredible patterns.
Patterns you'd never guess just by watching one bird fly.
Exactly.
Hmm?
In physics, it's similar, but with, countless particles interacting. Their complex dance leads the whole system to show properties that are fundamentally different from any single particle within it.
So is it like wetness? Wetness emerges from H2O molecules, but one molecule isn't wet. Is something like superconductivity just a grander version of that? Or is there something more fundamental going on?
That's a really good question. The wetness analogy gets the whole is different idea across, sure. But things like superconductivity or superfluidity, they're even more profound, I'd say.
How so?
They aren't just scaled up properties. They actually represent entirely new phases of matter. The rules are different. Properties that they defy the classical intuition we have based on individual components. They only happen because of this collective quantum behavior.
Wow. Okay. And this idea of emergence, it really seems to explode when we hit the fractional quantum Hall effect, the FQHE.
Oh, absolutely. That's where the weirdness factor really cranks up. It's another low-energy collective thing, lots of particles involved, kind of like a superconductivity cousin, maybe, but with this unbelievable twist. What's just mind-blowing about the FQHE is that new particles, or more accurately, we should call them quasiparticles, they literally emerge. They pop out of this collective soup.
Okay.
And these quasiparticles, they carry fractional electric charge.
Wait, fractional.
Yeah, like 1/3 or 2/5 of a single electron's charge.
Hold on. 1/3 of an electron's charge? My brain immediately goes to, like, chopping up an electron. Is that what's happening?
Yeah, it's a natural first thought. But no, that's the amazing part. The electron itself isn't being fractured or split.
And how?
Think of it more like, imagine a huge, swirling crowd of electrons. They're all moving together in this incredibly coordinated, intricate way. The collective motion itself acts just like a single new entity.
A quasiparticle.
Exactly. A quasiparticle that just happens to carry, say, E3 charge. It behaves as if it were a fundamental particle with that charge, even though it isn't. It's purely an effect of the group.
So the electron is still whole, but the effect of the group creates something that looks like a fraction.
Precisely.
Yeah.
And what's striking, the Nobel laureate points out, is that to understand this, the values of fundamental constants like E, the electron charge, or H, Planck's constant, they aren't even the main thing you need to focus on.
Really? How can that be?
Because it's the collective state, the emergent behavior that dictates the properties here. The effective charge is what matters in this context, not just the underlying electron's charge in isolation.
So what this fundamentally changes then, it's that the rules in these specific, maybe extreme conditions aren't solely dictated by the electron itself. It's about how millions of them collectively organize.
Exactly. It's a collective decision in a way.
That's huge. It's not just understanding nature better. It feels like a hint towards maybe designing materials with totally novel properties.
It really does. It shows nature has these tricks up its sleeve, creating behaviors that seem to just sidestep our basic particle definitions.
Okay, let's switch gears a bit, but stay on this theme of emergence. There's another really cool example, solitons in a polymer called polyacetylene.
Right. And this is great because it shows emergence isn't just confined to, you know, ultra low temperatures and high magnetic fields like the FQHE. This happens in a relatively simpler system.
Polyacetylene. What is that exactly?
It's basically a simple organic polymer. Think of a long zigzag chain of carbon and hydrogen atoms, CH units, linked together.
Okay, simple chain. So what happens there?
Well, when lots of these chains form a crystal, something quite remarkable can occur. The phonon, which is the basic quantum unit of vibration or sound in the crystal.
Like a particle of sound.
Sort of, yeah. At low energy scales, this vibration, this phonon, can effectively become a stable particle-like excitation called a soliton. And these solitons, they can move freely along the chain. And amazingly, they don't just decay or fizzle out.
Stable particle-like things from vibrations. Okay. And their properties are weird too.
Oh, they're wild. Absolutely wild. For starters, a soliton can carry a full electron's charge, positive or negative.
Without actually being an electron.
Correct. It's carrying the charge, but it isn't an electron itself.
Okay, weirdness level increasing.
It gets better. They can also carry fractional charge, like plus or minus half an electron charge, sometimes 1/3, 2/3, depending on the exact setup.
Fractional charge again?
And maybe the most bizarre property of all,
Mm-hmm.
these solitons can have a spin of 12, just like an electron,
Uh-huh.
but have 0 electric charge.
Ooh, hang on. Spin 12, like an electron, but no charge. My physics intuition just,
Yeah.
it feels wrong somehow.
Yeah.
I always connect spin and charge intrinsically. How does that even compute?
It's a fantastic question because it forces you to ask, what are these solitons, really? They're not fundamental particles. They're what physicists call topological configurations.
Topological, like geometry.
Exactly. Think of the polymer chain.
Mm.
The chemical bonds can arrange in basically 2 equally good alternating patterns. Let's say pattern A and pattern B.
Okay.
A soliton is essentially the boundary or the kink, the transition region, where the chain switches from pattern A to pattern B.
Ah, so it's a distortion in the chain's pattern?
Precisely. It's a structural defect, a shape in the lattice that moves. And its properties, whether it carries charge or spin or both or neither, are determined by the specific geometry of that kink, how the patterns meet.
So the properties emerge from the shape of the distortion, not from an underlying particle having those properties inherently.
You've got it. It's another powerful case where the collective arrangement, the structure, creates something that behaves like a particle with unexpected features. It just highlights the incredible complexity hidden in these systems.
It really makes you wonder what else is lurking in seemingly simple materials. So, okay, we have these amazing kind of baffling phenomena, FQHE, solitons. How do physicists actually connect the dots? How do they develop a framework to understand them?
One really important concept is something called adiabatic mapping.
Adiabatic.
Meaning,
Slow change, no heat exchange.
kind of. In this context, imagine you have your system in one quantum state. Now, you very, very slowly change the external conditions, like gently turning up a magnetic field or smoothly deforming the material.
Okay, like kneading dough slowly, as you said earlier.
Exactly. If you do it slowly enough, the system can smoothly transform from its initial state into a new state without any sudden jumps or disruptions.
Yeah.
This smooth transformation, this mapping between states, lets us relate different phases of matter. It's actually crucial for understanding the FQHE.
How does that help with fractional charge?
Well, it relates the complex interacting state of the FQHE liquid back to simpler non-interacting states in a way that preserves certain fundamental properties, revealing the underlying topological structure that dictates the fractionalization. It's a way to track what's fundamentally changing and what's staying the same, even if the details look very different.
And this links back to those Landau levels you mentioned for FQHE.
It does. In a strong magnetic field, electrons get forced into these discrete energy levels, the Landau levels. You'd normally think, okay, add some dirt, some impurities to the material.
And that should mess everything up, right? Scatter the electrons, ruin the clean levels.
That's the intuition. But astonishingly, for the quantum Hall effects, moderate amounts of disorder don't destroy the quantization. The plateaus in the Hall resistance remain perfectly flat.
They stay flat even with impurities. How?
It's a phenomenon related to something called the Prange effect. Essentially, the impurities can trap some electron states, but the extended states that carry the current find ways around them, preserving the overall quantized Hall conductance. It speaks to the incredible robustness of these quantum states.
It's deeply counterintuitive. Disorder usually kills delicate quantum effects.
Usually, yes. But here, the effect is protected, you could say, by topology. Which also brings us to another key idea, flux quantization, or gauge transformations.
Flux quantization sounds like magnetic fields again.
It is. Imagine threading a tiny, hypothetical tube of magnetic flux through your 2D electron system in the FQHE. Now, as you slowly increase the flux in this tube by one flux quantum, a fundamental unit, the system has to respond. The way the quantum state of the entire electron fluid changes, how its phase winds around that flux tube, directly reveals the fractional charge of the quasiparticles.
So inserting a specific amount of magnetic twist forces the system to show its fractional hand, so to speak.
That's a great way to put it. It's like a diagnostic tool. These concepts, adiabatic mapping, the robustness despite disorder, flux winding, they all point to the same thing. The physics is governed by the collective topological nature of the state, not just individual particle behavior.
This really feels like a major shift in thinking, doesn't it? Moving beyond just breaking things down to really appreciating how systems organize themselves, how the whole takes on a life of its own.
It absolutely is a paradigm shift. It forces us to accept that emergence is not just some curious side effect, it's a fundamental way nature operates. Understanding the whole is sometimes more predictive, more fundamental than just knowing the parts.
And what about the practical side? Does understanding fractional charges or spinless spin actually lead anywhere useful?
Oh, immensely so, or at least the potential is immense. Understanding these collective quantum phenomena is crucial for material science. Think about high-temperature superconductivity. That's another profoundly emergent phenomenon we still don't fully grasp.
Could insights from FQHE help there?
Potentially. The underlying principles of collective behavior, topological states, how particles conspire to create new properties. These ideas could unlock pathways to designing materials with desired traits, whether it's lossless electricity transmission or, say, components for quantum computers.
Quantum computing feels like a natural fit, needing these robust quantum states.
Exactly. Topological quantum computation relies on precisely these kinds of robust, fault-tolerant quantum states, potentially based on quasiparticles like Majorana fermions, which share some conceptual similarities with these emergent entities. The better we understand emergence, the better equipped we are to try and engineer it.
And it's probably important to remember these aren't discoveries made by one lone genius in a lab, right?
Absolutely not. That's a crucial point. The story of FQAG, of solitons, it involves decades of work by numerous brilliant physicists, experimentalists, and theorists, people building on each other's findings, challenging ideas, collaborating.
It's a real testament to the scientific process.
It truly is. This kind of deep insight rarely comes from a single mind working in isolation. It's a collective human effort to understand a collective natural phenomenon.
So wrapping up our deep dive today, we've journeyed into this fascinating world of fractional quantization. We've seen it's not just some obscure corner of physics.
No, it's really a window into a deeper principle, that the universe is constantly surprising us, creating new kinds of order, new entities, new rules, just from the complex dance of many simple parts interacting.
It shows how seemingly simple systems can harbor this incredible, unexpected complexity.
Right, and it forces us to look beyond just the fundamental particles and constants sometimes.
Which leads to a final thought, maybe. If things we thought were bedrock, like the electron's charge E or Planck's constant H, aren't always the most relevant parameters, if collective behavior can conjure up these bizarre new forms of matter with fractional charge or spin without charge.
Yeah. It really makes you wonder, doesn't it? What other everyday systems, maybe even things we think we understand well, might be hiding their own complex emergent secrets? Secrets that defy our current picture of fundamental reality.
And pushing that further, how might this shift towards understanding emergence change our whole approach? Could it be the key to tackling huge unsolved puzzles, like unifying gravity and quantum mechanics? Or could it unlock completely unforeseen technologies down the line?
It's impossible to say for sure, but it definitely opens up thrilling possibilities. It suggests there's potentially a whole universe of emergent phenomena out there, waiting to be discovered and perhaps harnessed. It's a reminder that the fabric of reality might be even richer and stranger than we imagine.